Ever looked up at the night sky and wondered how the sun and stars keep burning? This question has sparked curiosity and fascination in humans for centuries. The twinkling stars, the radiant sun, they're not just celestial decorations. They're fiery performers in the cosmic theater, continuously dazzling us with their incandescent dance. But have you ever stopped to ponder what's fueling this seemingly eternal spectacle? Stars, including our sun, are celestial powerhouses burning every second of their existence. They're not like your average fire that needs oxygen and fuel. No, they operate on a grander scale, a nuclear scale. Their fuel is not wood or coal, but elements, and their process of burning is not combustion, but nuclear reactions. Now you might think, nuclear? Doesn't that mean they should explode or something? Well, not quite. Stars, despite their blazing appearance, are quite the controlled reactors. They balance their immense gravitational pull with the outward pressure created by their nuclear reactions, maintaining a state of equilibrium. This delicate balance is what allows them to shine for billions of years. As for our sun, it's a star too, albeit a closer one. And just like other stars, it's burning right this moment, converting millions of tons of matter into energy every second. You feel its warmth on your skin, see its light brightening your day. That's the sun's energy, produced by its continuous nuclear reactions, reaching us after an 8-minute journey across the vast expanse of space. So what's the science behind this celestial burning? How do stars manage to burn for such a long time without running out of fuel? And what exactly is this nuclear reaction we keep talking about? The answers to these questions lie in the realm of nuclear physics, in the concepts of nuclear fusion and fission. These are not just scientific jargon, but the fundamental processes that power our universe. They're the reason why stars shine, why the sun warms our planet, and why we're here, pondering the mysteries of the cosmos. To unravel the mystery, we'll dive into the world of nuclear reactions, namely nuclear fusion and fission. So what exactly is this nuclear fission? Sounds complex, right? But worry not, we'll break it down. Imagine you have a large, unstable nucleus. This nucleus isn't happy with its current state. It's like a giant boulder perched precariously on the edge of a cliff, ready to fall. Now what happens when you give that boulder a little nudge? It splits apart and tumbles down the cliff, right? That's exactly what happens in nuclear fission. The heavy, unstable nucleus is split into two lighter nuclei. This splitting or fission can happen spontaneously, but it can also be triggered by the nucleus absorbing extra particles like neutrons. Now here's the exciting part. When this large nucleus splits, it doesn't just break apart quietly. Oh no, it releases a considerable amount of energy. And when we say considerable, we mean it. The energy released in nuclear fission is 1,000,000 times greater than that released in chemical reactions, which are the ones you'd see in a high school science lab. This is the principle behind nuclear power reactors. They harness this energy to generate electricity, powering up cities and towns. But where does this energy come from? It's all about mass. Remember Einstein's famous equation, E equals mc squared? Well, in nuclear fission, a tiny amount of mass is converted into energy. This might seem like magic, but it's just physics. And it's this energy that's harnessed in nuclear power reactors. So nuclear fission is all about breaking things apart, but not just any old breaking apart. It's a process where a heavy, unstable nucleus splits into two lighter ones, releasing a massive amount of energy. It's like a controlled atomic explosion right here on Earth. And it's this process that powers our homes, our cities, and our lives. So in essence, nuclear fission is all about breaking apart and releasing energy. Now that we understand fission, let's shift gears to fusion, the second type of nuclear reaction. Nuclear fusion, in contrast to fission, is a process where two light atomic nuclei combine to form a heavier nucleus. Picture two dance partners coming together in a spectacular whirl, creating a more substantial entity. That, in essence, is what nuclear fusion is all about. You see, it's the exact opposite of fission. While fission is like a heavyweight boxer breaking apart a punching bag, fusion is more like a romantic dance where two lighter elements come together to form a heavier one. Now you might be wondering, where does this fusion happen? The answer is all around us, in the stars, and most importantly, in our very own sun. Our sun, a glowing ball of gas, is essentially a giant fusion reactor. Every second, millions of hydrogen atoms in the sun come together to form helium, a process that releases an enormous amount of energy, enough to power the entire solar system. This energy is what makes the sun shine, and it's what gives life on Earth. It's the heat that warms our planet, the light that illuminates our days, and the vital ingredient for photosynthesis, the process that allows plants to grow. But the dance of fusion isn't easy. It requires extremely high temperatures and pressures, conditions that are naturally found in the core of stars. That's why fusion is often referred to as the power of the stars. As we speak, scientists and engineers around the world are working tirelessly to replicate this process here on Earth. Imagine a power source that uses the same process as the stars, providing us with nearly limitless clean energy. That's the promise of nuclear fusion. So to put it simply, while fission is about splitting, fusion is all about combining. It's a dance of atoms, a dance that powers the stars and potentially our future. Now, how does this all relate to our sun, the glowing orb that gives us light and life? Well, our sun is essentially a massive nuclear fusion reactor, a colossal powerhouse that ceaselessly churns hydrogen into helium. This process is not just a simple chemical reaction, it's a dance of atomic particles under extreme conditions. Picture this, deep within the sun's core, where temperatures reach a staggering 15 million degrees Celsius, protons, which are hydrogen nuclei, move so fast that they overcome their natural repulsion for one another. They collide and fuse, forming a heavier particle known as a deuteron. This process also releases a positron and a neutrino, but let's focus on the deuteron for now. This deuteron then collides with another proton, creating helium-3 and releasing a gamma-ray photon. When two helium-3 atoms collide, they fuse to create a helium-4 atom and two protons. This final step completes the cycle, known as the proton-proton chain reaction. What's fascinating is that each of these fusion reactions releases energy, and it's this energy that we perceive as sunlight. The gamma-ray photons produced in the sun's core take thousands of years to reach the sun's surface. But once they escape, they race across the solar system and reach our planet in just over 8 minutes. This sunlight is more than just light, it's the lifeblood of our planet. It drives photosynthesis, allowing plants to grow and produce oxygen. It warms our world, creating the conditions necessary for life as we know it. The sun has been performing this fusion dance for about 4.5 billion years, and it's got enough hydrogen fuel to keep going for about 5 billion more. Every second, the sun converts around 600 million tons of hydrogen into helium, releasing a mind-boggling amount of energy in the process. So, the sun is basically a giant fusion reactor, continually converting hydrogen into helium and providing us with warmth and light. We've traversed the path of nuclear fission and fusion, but what does this all mean for us and our universe? Let's take a step back and recall. Nuclear fission, the splitting of a heavy, unstable nucleus into two lighter nuclei, and nuclear fusion, the process of combining two light nuclei to form a heavier nucleus, are the fundamental processes that power the universe. In the heart of stars like our sun, nuclear fusion is the engine that fuels their glow. Hydrogen atoms under immense heat and pressure coalesce to form helium, releasing a colossal amount of energy in the process. This energy radiates out from the star's core, eventually reaching us as heat and light. Now let's bring it down to Earth. Nuclear fission is the process harnessed in nuclear power plants. When a neutron strikes the nucleus of an atom of the isotopes uranium-235 or plutonium-239, it causes that nucleus to split into two fragments, which are in turn radioactive. This chain reaction releases a significant amount of heat, which is used to generate steam and ultimately electricity. Imagine a future where we can master these processes to our advantage. The potential implications are staggering. If we could safely and efficiently perform nuclear fusion here on Earth, we could have an almost unlimited supply of clean energy. This would revolutionize our power supply, reducing our reliance on fossil fuels and significantly decreasing greenhouse gas emissions. But it's not as easy as it sounds. Achieving the conditions for nuclear fusion is a monumental task. It requires temperatures and pressures that are difficult to sustain on Earth. Nevertheless, scientists and engineers around the world are tirelessly working towards this goal, inching us closer to a potentially brighter and cleaner future. So, the next time you gaze at the stars or feel the sun's warmth, remember, it's all thanks to the incredible power of nuclear reactions.